Hello, everyone. Welcome. My name is Srikanth Mandke, and I am a software development manager here at Amazon Marketplace. Me and my team built a document management service. We built it for our initial use cases, and we built it quite small. So at that point of time, we built it with Oracle as its database, and we were using Oracle in the active and passive mode. As soon as the service was launched, we saw phenomenal adoption. We were seeing 500x growth year-on-year basis. And within the first 18 months, we realized that we would have to change our primary data store. And hence, we decided to move from Oracle to DynamoDB. At the same time, the number of new use cases that had been onboarded onto the platform were of business-critical nature. That's when we realized that we would have to do the migration right without any downtime. This talk is going to summarize all the learnings that we got from doing this migration. It is going to be right from beginning all the way to the end. And this is meant for anybody else who is trying to do this migration in future. Just to get a little bit of understanding of the audience here, how many of you are just using relational databases? Fair? And who are using a mix of both? A lot more? Great. And how many of you are considering migration in the next short time, right? Might be the next 1 or 2 years. OK? Large number. Great. This talk is really going to help you to think about every aspect of what you might have to undergo, face, think, plan for doing this migration. With this material, you would have clearly understanding of what it will take, how you could go about doing it, and what are the things you might have to consider. Again, I just put a caveat that this is going to be a template. This is how we did it, but you will have to tweak it a little bit for your own needs. And this is not a talk on Oracle or DynamoDB. I expect a fair amount of knowledge of both of these products, so I'll not be going into any details of them. Second, I'm not taking any sides. We basically think both technologies and products have their own sweet spot. And finally, I will talk about a little bit of how we went about our schema, but it is not a primer on how to do non-relational schema design either. Fair. So this is what we are going to follow. So I'm going to give you a brief overview of the application so that it sets your context. Second, we will talk about the different steps that we took for our preparation, and those might be things that you might have to consider when you are thinking about your own migration. We'll talk about how we went about transforming our schema, the different migration strategies that we considered, and their pros and cons, and the ones which we went with. We will talk about how we refactor our APIs. We will talk of the actual data migration itself, and then we'll give you a little bit of the results. Fair? So application overview. Ours is a document management application. So we receive documents. We manage the documents and metadata. And we give the documents to whoever deserves them or who has got authorization for them. There's 3 services. The document ingestion service is responsible for receiving the documents. The document manager service manages the metadata, the attributes, the permissions, the configurations. The distribution service is responsible for distributing the documents to the clients. The documents are themselves maintained in S3. They are encrypted and kept. And all of the document metadata, the permissions, ACLs, are managed in the Oracle database. And this is our primary database, and this was the database that we were trying to migrate. So this is what we hope for. We just have DynamoDB, and we are good. So let's kind of look at the reasons why we had to migrate. First, availability. As mentioned, we had Oracle in the active and standby mode when we initially started off our application. And we had to flip the database from time to time to apply security patches. And just the amount of downtime that was required to flip the database was not meeting the needs of the business-critical use cases that had been onboarded. So the business use cases needed 5 nines of availability at least, because we were even supporting the Amazon retail pipeline. So that was less than 10 minutes of downtime and 0 planned downtime. We couldn't meet it with what we were trying to do with our current state. Scalability. We were seeing 500x growth year on year. And since the start of the service, we expected to cross like a 10 billion in the first 4 years. So it was something which was phenomenal. We were not planning for it when we started off. Otherwise, we would have thought of it differently. Operations. As new use cases came on and more data was added, we always needed the DBA to tweak the partitions, manage the indices so that we could get the really good, consistent throughput from our database. But we really liked the fact that DynamoDB would allow us to scale our reads and writes quite easily. So that was a very attractive feature. Finally, cost. We looked at running Oracle in the active mode, and we looked at using DynamoDB. And it was quite clear from our analysis that DynamoDB was going to be a little bit more cheaper or less expensive. So those are the reasons why we migrated. So what were the steps that we took as a preparation for the migration? First, me and my team were the people who built the application, but over a period of 1 to 18 months, we had made a lot of changes to the data. We had foreign key constraints that were different. There was changes in null handling. There were differences in how we managed some columns. Some of them were changed from the data types, strings to ints to Boolean. We had to deal with entities and every variation of the entity in all of its forms in the existing database. And that was a challenge because even though we built the application, we were not sure that we knew every variant of every entity in our own database. And that is a challenge you're going to face too. The way we tried to just think about it was, let us sample data or entities every 15 days and create a test bed and see that we could migrate at least these entities. So that was the basic starting point for any migration. We created approximately 5 to 6 million entities with all of its different variants. And by sampling data all the way from the start of the service till today, and use that as the basis for starting off. Second, when we are trying to migrate off a particular database like Oracle, we are not just talking of moving away the data. Usually we have a lot of information in the stored procedures, in the jobs, in the scheduled jobs, the document transformations. All of these processes need to be migrated too. One of the things that we did was to move all of these things into APIs. We moved all of the business logic out of Oracle into the application logic. And all database interaction was limited to the most basic operations: read, write, update, or delete. And that is how we prepared ourselves to do this migration, because we had moved out all of the business information out of the database. Just to give you an example, here is an example of one of our APIs. This API is talking to 3 different databases. And this API is updating tables. We would know what amount of data being written to each of these tables, how much data was being returned, in what order. So this helped a way to know this is what the process that I'm trying to migrate from Oracle to DynamoDB. So we had this for every API that we had, so that we know that at the end of it, each of these processes would have a store in DynamoDB. Traffic. Any application sees a variation of traffic patterns. Might be just varies by time of day, sometimes by period of the year, and we really needed to kind of think of the application that would be able to manage the traffic over a period of time, because data migration takes months or longer depending on the amount of data. So we analyzed the traffic for the last 3 months, and we figured out which of those traffic patterns put the most stress on our own database and on the application. So these are the different sessions, or these are the different patterns of traffic that were supported on our application. And we looked at this distribution, and we figured out which distribution would have the most impact on our application. We chose exactly those patterns which would apply the most stress as the basis for migration. So when we were going to do stress tests, we would figure out the pattern which was going to apply the most stress. To that, we added our migration traffic, and that was the minimum threshold that the application had to reach for it to be able to successfully migrate. We went further. From the sessions, each of those sessions could call multiple APIs, and we brought it down to each API level. What would be the pattern of APIs we would be calling at any point of time? And this is what we stress tested it for. So we had the complete information of what we were going to stress our application down so that we knew that we would be able to successfully migrate. Finally, we froze the schema for the duration of the migration. We knew that we couldn't kind of have a dynamically changing schema. What we did was we planned all of the features requests that was going to require a feature change all up front. We completed them. We froze the schema, and we told our clients that we would not be able to onboard any new requests that require a schema change till the end of the migration. And finally, we communicated to the clients. So they were in sync with what we were doing and why we couldn't make any changes to schema. So those were the preparation steps. Now moving on to the schema design. In true Amazonian fashion, whenever there is a complicated problem, we first come up with tenets. And these are guiding principles which we use for any complex project. So we always use them. This is what we want to achieve, and this is why. We then make the design, and we validate that the design is meeting the tenets. If the design matches the tenets, then we know that we are complete. Else we iterate again and again until we know that all the tenets are met. So it's an iterative process. We did not get the schema in the first shot. We went through several iterations before we got to where we wanted it to be. But these are the tenets that helped us. You might have to design your own tenets if that is how we'd go about designing. Optimize for scalability. Yes, we were migrating very clearly for speed and scalability, because that is why. Now, we were going to design it so that every operation would be as fast as possible, would be able to update as less data as possible, and we were not going to consider using third normal forms as we did when we designed Oracle. The design of the APIs would design the database schema and not how we wanted to store it, clearly. Second, we chose eventual consistency only because when we use consistent reads, all reads in DynamoDB go solely to the master, which itself becomes a bottleneck, and we did not want to have that. So anytime a client wanted to do a read after write pattern, they would have to redo and ask the query again if the data was not there. But we did not support it in the application itself. Idempotent, we were a distributed system, and we expect failures in a distributed system. So we had to make sure that an application, even if it failed, would be able to recover gracefully from that. Immutability. We were going to use the insert-only pattern. That is, anytime we updated any entity, we would not update the entity itself. We would insert a new row and update a pointer to the latest. And we were doing this for audit. We needed to maintain every historical change made to every entity. Single table writes. This is again for performance. We were hoping that any API would be able to just write to one table or just read from one table. That was our goal. We knew it was aspirational. But anytime we knew that we had to write to multiple tables, we ensured that the first write would have the data to use so that it had all of the superset of data that would be updated to any subsequent tables. The reason for it is that we could do read repair, even though the next operations failed. And I will talk a little bit more of this later on in the talk. Just to give you a little bit of hint of our schema, the document class, let's say it represents, let's say, a passport. So all passports would be a document class called passports. My own personal passport would be the document. I might have to update my passport, let's say after 10 years after it expires, and I've got a second copy or a second version. That would be in my versions. I might maintain my passport either as a PDF file, JPEG, PNG, and that would be the locators. The locators told me what is the different files actually stored for it. And metadata. So this is a key value pair. So for every file type, we could store like, oh, this is the size, this is the type, this is the resolution. All of those would go into the locator metadata. At the same time, the document version metadata could have, for my passport, place of issue, date of expiry, those kind. So this was, again, a key value. So this would show the approximate way we stored metadata before. And this is the white table that we came up with. Let me go through it piece by piece. First, so here we have the locator and metadata being stored. And we see the locator ID is always a UUID. And you'll notice that in this table, there are UUIDs everywhere, because we did not want any hotspots. Second, the version metadata. So all the key value became a JSON blob, and we stored it. The document version itself, that became our partition key. That is the UUID. And we had 5 indices in Oracle. And those became our 5 columns in the documents table. And then the document and the document class became these 3. So that's how all of this data became into one wide table. But we also had specific tables to support the different operations. And all the information stored in the documents table was redundantly stored in the user attributes and the document attributes table. These were built specifically for supporting different operations. And I will talk about these operations a little bit later. First, we use the user attributes table to search. And that is why we see the GSIs on it. It doesn't mean that all of them have to have 5 GSIs, but there's a maximum of 5 GSIs as the DynamoDB limitation. And we use the same document UUID, document version UUID, as the partition key. This had user metadata. So for example, if I was trying to store the status of my document, so if has it been reviewed by somebody or not, those are the things that would go into the user metadata. At the same time, my passport might be valid for 10 years after that is expired, and those would go into the document lifetime data. And we would have completely different APIs to support each of these operations. So it is never the one operation that is trying to get both the data. Depending on what you're trying to do, you would either go against the user data or the lifetime data. This is how we handle the multiple writes. So whenever a client writes to the API, we write to the documents table. We get a document version ID. And once we have the document version ID, we write to the user attributes and the document attributes table in parallel just to save time. It's only when all of them are successful that we return back to the client. Now, anytime there are writing to multiple tables, there is a chance for failures, and it is expected. So yes, we totally handle such kind of failures, and this is how we handle those failures. Anytime we read a data, we first check Did I find it in my user attributes table? If it is not there, I go back to my original table, which is the documents table, get the data from there, put it into the user attributes table, and return it. So by doing read repair, even if there are failures in updating your multiple tables, we are able to rectify the problem. And we use read repair in several places. A very common pattern we use everywhere. Now let's talk about the second aspect of the problem, which was we were following an insert-only pattern. Let me kind of show it with a better example. Here is a table which has got the UUIDs, if you notice, are all the same. So that would be my document version itself. So it could be my passport. There are 2 copies. The UUID version 1 is the first entry of it, and that's why the previous version is null. Then UUID 2 is the later version. And the head row is a special row. The head row always points to the latest version of the record. And it is only this record that is updated. There are no other records anywhere in the database that get changed. So let's see how a new insert happens into this table. Well, now I insert version 3. Its previous version is v2. At the same time, the head is not yet updated. So if you search at this time, version 2 is still the latest. And finally, we update the head to v3. At this point of time, version 3 is what you would recognize as the latest version. But this is how we follow the insert-only pattern. So every version of every change to every entity is maintained. OK. So let's review. We talked about our tenets. We then talked about how we kind of came up with a wide schema. We talked about how we write to multiple tables, how we use read repair to rectify problems because there is no ACID support in non-relational databases. And then we talked about our insert-only pattern. And we also talked about how we optimize performance by having specific tables specific to user operations. So let's move into the next section, which talks about the different migration strategies. Just to give you a little bit of introduction to what I define by phases. Data was originally only in Oracle, and that's phase 1. That is the existing behavior. And we wanted to finally have all the data go into DynamoDB. That's the final phase. And the phase 2 and phase 3 are how we get there. First, we move the application so that we start writing to both Oracle and DynamoDB, so that all new data goes into both. And at that point of time, Oracle is considered the master. So in case there is any variance, we kind of go against the data from the master. Then we do the backfill of the data from Oracle into DynamoDB. And once DynamoDB is caught up, we then switch. We maintain this to make sure that there are no mistakes, no errors. And finally, when we're convinced that everything is good, that's how we're going to take off. So these are the phases. And we move between phases through configuration. So it is not through deployments, because we take approximately 1 or 2 days to do our deployments in 4 realms, and that would be too time-consuming in case we had to do our rollbacks. So when we started off migration, all the 4 phases of data, the code had how to handle all 4 phases at that point of time, and we would just migrate by using configuration. So I'm also kind of talking now about a few ways to evaluate how we are going to evaluate the different migration strategies. So that's how application consistency. All client applications should see the same uniform behavior across the migration, independent of phase, and that is expected. That's application consistency. Second, correctness. At the end of it, the expectation for the data in both stores is that they are the same. Completeness. We need to know that every entity in Oracle has been migrated to DynamoDB, and we need to actually verify that it is all migrated. And finally, even though we plan for the best, we have to design for the worst. So we should assume that we would not be able to do things completely in the first round, go back to a last known good, fix the problem, and continue. So any migration strategy should be able to be restarted successfully. First one, workflow. A client writes to the workflow engine. The workflow engine puts it into the queue. Then we have workers, and then the workers take the responsibility of writing to databases. And then we read from both of them to make sure that the data being written to both of them is the same. And once we confirm that both the data and the entities are the same, we say it is successful. So this is our workflow model. So let's see why we did not use it. First, data was written to the workflow, and the clients have got a success. So if the workflow engine is backlogged or is stuck, you would never be able to get the data from the stores because neither of the stores, either Oracle or DynamoDB, do not have the data. Second, if there are multiple updates going on simultaneously, the workflow engines do not ensure the same order. So it is a possibility that read 2 happens later than read 3, or update 2 happens after update 3. So the data finally might be wrong. Finally, if we are always reading from both stores to make sure that we have written data carefully and correctly, but if you're verifying for version 1 or update 1, update 2 or update 3 might have started. So you might be comparing data in Oracle with version 1 with update 2 or update 3. Now, this could lead to false positives or false negatives, which is unacceptable. We actually ran this, and the amount of data errors we were getting were unacceptable for our application. And that is why we did not use this method. So just to kind of give you an example of how we are using these criteria, the complexity is low. App consistency is not meeting because the final state, if then update 2 happens earlier than update 3, it would not be correct. Correctness is the same. Completeness, we could always ensure because once we know that workflow is completed, all of the rows, it is complete. Potential data loss is mainly because, again, due to correctness. Restartability, we can always restart the workflow, and latency. So this is how we kind of use these evaluation criteria so I could go fast in the next iterations. So first, what were the problems with the single master model? Means with the workflow model was we were writing to a separate entity and not writing to the actual databases. So first, now in the single master model, we use the client to write directly to the database itself. And if there are multiple updates happening at the same time, we use conditional puts to make sure that only one of them happens at a time. So we address both of the problems for the workflow model. So let's see how this thing works. So whenever an update comes to the service, now the service would, and the entity shows that this record is right now in Oracle. So the update goes to where the entity is. So it goes first time to Oracle. Now, if the data was migrated over, the next time an update to the entity happens, it would go to DynamoDB. So this is how the simple single master model worked. The main problem we found was there was no means to verify that the data written to DynamoDB was correct or not because there was no baseline. Unless we were able to compare it to something which we know was good, there is a potential that what we have written would not be correct. And that is why we abandoned this model. Two-tracking model. So to improve on the model, we said we needed a baseline, so we started writing to both the stores, so both Oracle and DynamoDB. And since we are writing to 2 stores, we added flags to the entities in both sides. One, who is master, and is the row being backfilled to the other data store or not? So we had flags both in Oracle and flags in DynamoDB. And the reason we had flags in both sides is because in case there was a rollback, we might need to move data from DynamoDB back to Oracle. So that is why we had flags in both sides. And just to kind of give you a high-level view of the client writes to the master flag is set and for that row. Then secondary data gets updated. Then once it is written to the secondary, we write the backfill. And then only then is the client sold, it's done. But this model is a very simplistic approach to what the problems are in this. We have spent days with this model trying to deal with all of the edge cases. And it is quite difficult to make sure that we have handled all of the edge cases. Because every time we consider edge cases, we need to think about we might have to roll forward, roll back because of errors. There might be potential loss of data. So even though this model was great, we could not convince ourselves that there would be no loss of data. And there is a reason for it. One, we found that when we had to put an index on the GSI just to know that has this row been migrated or not. And when we put this GSI on the row, we found that that became the bottleneck because this was a low cardinality field because it had only 2 values. So for the volumes of data that we were managing and the rate that we needed to get to, by just having this GSI, we just did not get the rates we needed. Second, we were already using all of the 5 GSIs because we had 5 index metadata in Oracle. So we couldn't add a 6th GSI to the same table. And we were forced to use a secondary table for that. And any table which is a secondary, there's a chance that it might not get updated because we are not getting asset properties. And that is the reason why, even with our best intentions and efforts, we could not get this mechanism to work for us successfully. We can talk about this later if you wanted more details, but I'm going to kind of move on at this point of time. So the implemented model. So what were the improvements to this model? First, the limitation was that we could not have GSIs on the flags in DynamoDB. So first, we moved all of the flags for is it master from the data into the code. So the code knew if it was working in phase 2, that Oracle was going to be master. And if it was in phase 3, DynamoDB was going to be master. So that's how we eliminated one flag. The second flag was, is it master? And this was related to, in case we needed to roll back from DynamoDB back to Oracle. So how did we minimize the chance for rollback? We took a penalty in terms of validating each row. So whenever we wrote a row to any data store, we read it back. We compared it with the base, which was Oracle or DynamoDB. And only when the comparison said that both entities in both the data stores were consistent, we then returned a success to the client. So by adding a performance penalty to our application, we minimize the need to roll back from phase 3 to phase 2. So the only portion that we needed to really migrate was the historical data which was in Oracle before the migration. So for doing this migration, we just needed one flag in Oracle. Is this entity being backfilled or not? And that is what we did. So we just added a single entity in the Oracle side for checking if the migration of that entity was done or not. So let's look at it further, right? I also would like to call out, there is a small chance of inconsistent data. Let me explain. Whenever you're writing to 2 data stores, there's a potential that you might not be able to write to the other just because of distributed systems and failures. And we would not return a success to the client, but there's a chance that this row got orphaned in the master. And we were OK with this because this row would get purged through the lifetime retention policies, might be a little bit later, but that would be just a row which would be a redundant row in our store. And we were OK with this redundant data being there. There was also a possibility that this redundant row would be discovered by a search, which asked for, give me all the rows for a particular service or entity. And we were OK with this redundant row being discovered too, because anytime they tried to do anything with it, they would discover that this was not a useful row because they would not have a corresponding correlation. Both of these things were acceptable. So let's see how we did the right. In phase 1, we were just writing to Oracle. In phase 2, Oracle being master, we first wrote to Oracle. And then we marked that is Dynamo backfilled to no. Then we wrote to DynamoDB. And once we have written to that, we mark that, oh, this row has been backfilled. We compare the two entities across the two data stores. And only when they say they're consistent, we say good. So that's how we did it in phase 2. In phase 2, this is where we do the backfill of all of the data. This is just a marker for that. Phase 3, we follow a very similar pattern. It's just that now, since DynamoDB is the master, we first write to DynamoDB, but essentially the same pattern. And finally, in phase 4, we're just writing to DynamoDB. And a very similar model is used for read. We read only in Oracle. Again, when we are doing a read, we first read Oracle in phase 2. And if the data has not been backfilled, we write to DynamoDB, is it backfilled? And we'd read. So, and then we compare the two entities and then return back. So in case it was not backfilled originally, we do this read repair pattern again to fix it. Similarly, in phase 3, we do the same pattern in the opposite direction, with DynamoDB being the master. Finally, in phase 4, we're just reading from DynamoDB. So that's how we did our read and writes. Now, again, this is a simplistic model. I have not kind of shown you all the edge cases, the error handling, the exception handling, but this is the basic pattern. Again, to evaluate, the complexity is high, but everything else was good. Latency is the place where we pay the penalty for. We have higher latencies due to multiple reads and writes, which we are doing. So though that was the penalty we paid, but apart from that, everything was what we were hoping for, and that is why we went with this pattern. So we looked at the different patterns. We looked at some of the commonly used ones, the workflow, the single master, the two flag, and then finally a morph version of the single master, the two flag model that we implemented. And we gave you the reasons of how we went evaluating these strategies. We actually wrote and worked with each model to see if it was working or not before we moved on to the next one. Let's move to the next section now, the API refactoring. We use the adapter pattern to work across all the phases. So when the code was put in, it had information of how to work in phase 1, phase 2, phase 3, phase 4. And by a mere change in configuration, we could instantaneously move in the behavior from how it would do from phase 1 or phase 2. So we could do our roll forward or roll back quite immediately. And we had our basically persistence model being defined by the Oracle DAO or by the DynamoDB DAOs. So a very easy adapter pattern that we use, and that is how all of our APIs were built to do the migration. Okay. Now, let's actually talk about some of the things of data migration itself. So before we did our data migration, we looked at several things before we started off. So before we started off, we ensured, had we done the data migration successfully on sample data or not? And to do this, we had actually built a data migration tool. Now, this was a tool which we built custom for ourselves, but this tool ramped up or down the traffic, or migration traffic, in the exactly opposite direction as the production traffic. Now, the reason for this is if we did the migration of data only in the off-peak hours, it was going to add several months to our own migration time frame. So it was a really big saving and investment. This tool really paid off. Second, we had tested out our rollback scenarios in case of failures. So we not only tested out the happy path, which was going from phase 1, phase 2, doing the backfill, phase 3, and phase 4, which was the ideal one, but we assumed we could fail in phase 2 and we would have to roll back. We actually tested it out. Similarly, in phase 3, we could have failures, roll back, and go. So we actually went through this thing twice to make sure that we could successfully do a rollback, go to a last known good, move forward from there, and not have any loss of data. Check there was no loss of data, and we used 5 million rows. Third, We run stress tests in every phase. I think this is very key, that we ran stress testing in each phase. The read and write patterns in every phase are different. And you need to make sure that you are able to handle the peak loads of data from production traffic and your migration traffic in each phases. To do that, we had built a specific stress test tool. At the beginning, as a part of preparation, we had collected the different sessions that were the most impactful, and that's exactly what we used. We chose the most, those sessions which had the most impact on our database and application, add the migration traffic, and use that to stress test in each phase. So at the end of each phase, we knew that we could handle the expected max production volume in the worst traffic, and we had whatever migration traffic that we were planning on adding on to the application. Third, the read and write throughputs had to be really adjusted for DynamoDB. And this is what we did. I know it's a really busy slide, but let me walk you through it. Here is API, the create document, and we were expecting TPS of 400. We are writing approximately 8K, and that's why, based upon the read units for DynamoDB being 1 KB, it's 8 times that. And we were writing in this operation only one time to the table, and that is why for this operation we got the write units of 3,200. Then, since we were only writing once to the GSI, it became 400. And for the same operation, how we were writing the user attributes table, we talked of the different size and operation multipliers, and that's how we got the different values for each read. So this is our theoretical calculation of what we were expecting for each API. And we had all of the APIs, and this is what the peak values were expected. So we had, at the end, the total of exactly what each read and write units should be set for each of the tables. So when we actually ran our data migration tool, we would confirm that the expected GSI settings and the actual theoretical values matched, so that we knew that we would not get throttled as a part of migration at any point of time. We made mistakes in this process, and this exercise really helped us. We did discover a few places that we had underestimated what the read units and write units needed to be, and we were able to correct it based upon this. We now knew the different values for the latencies in each phase, and we updated our operational and alarms dashboards so that we would know if we were behaving in the expected manner or not. And finally, we informed the same things to our clients because we had SLA guarantees with our clients so that they were in sync with what were the new updated SLAs for the time. Timeline. From start to end, we took approximately 9 months, and the schema was frozen for 6 months. So that is just a rough guideline. This can change. Again, we planned, we had 4 realms, and we were migrating data in 4 different realms. We had planned all of the migration to take place in a month, but it took twice as long, just because production traffic was high, and we couldn't get the migration traffic to reach the levels we wanted it to. Third, code. We had to build in code for each phase of the migration at this time, and that increased our size of our code 3x. And just to verify that the code was behaving correctly in each phase took us quite a bit of time. We took 3 weeks just to verify that migration code was correct. And finally, when we've completed data migration and we were in phase 3, we kept it for 2 weeks running in that phase just before we kind of removed Oracle completely, just to be a sanity check for our side. So now let's kind of talk about the results. We were able to complete the migration in happy path, no resets or no rollbacks. We were really thankful for it. There was no loss of data or errors, and we migrated 500 million entities very successfully. Let's evaluate the reasons to migrate and where we are today. Since the migration, we have had 100% availability. So the first reason to migrate, we have successfully managed very successfully. Second, we have got 10x more data, and we are seeing there's ample headroom. So we can keep on scaling with DynamoDB. And finally, we do not have a DBA. So I think we have brought down our costs, both from operations and from the ownership point. Suggestions. We ran the first time migration from the primary, and it became a bottleneck. We then moved to the different server and did the migration. It was far better. We got much better performance. Again, avoid GSI and low cardinality. This was really a bad problem, and that is the same reason why we couldn't kind of use the two flag model too. Really be careful of this one. If you need to, you might want to move your search to a cloud search or Elasticsearch. And this was another thing which you learned the hard way. When you scale for migration, do not overscale, because when you actually bring down the throughputs, DynamoDB does not collapse the partitions. So if you might have very low throughput on the partitions afterwards, and that can lead to hotspots in the partitions, even though you have sufficient read and write throughputs at the table level. So do not overscale just for migration. Well, that is what I had. We can take Q&A. I've got parts of my core team here who did the migration, so we can all take answers if you have any. Otherwise, thank you. And